Okay, this is for Samraj, Jacob, Forrest, Lucille, anyone else who missed the lesson on logistic growth functions. Okay, so I'm going to send you this handout and you're going to follow my pen. Okay, so the first thing I had the class do was I said just ignore all these words here. I'd like you to please solve this differential equation. And you're going to notice that it involves separation of variables, okay? So your classmates were all just kind of working. I said, okay, are we done yet? And they all said, yes, we're done. And I said, solve for y, and they got here. So you want to make sure you're pausing me accordingly so you kind of get the full experience. And I said, remember that you have this little algebraic trick, e to the kt plus c. I can write this as e to the c times e to the kt. And this is a constant in and of itself that we're going to write like this. Now, this doesn't mean that this c is this c. We're saying that at the end of the day, when I solve this differential equation, and again, we treat k as some unknown constant, okay, we get this solution, y equals c e to the kt. And what this is, we all noticed, was that, oh, this is an exponential growth or a decay function depending on the value of k. So this lesson that you both missed, that you all, 4 of you missed, is I gave you 2 shortcuts. One shortcut is a take it or leave it with a cost of about 3 minutes. That is this shortcut. So the shortcut here is whenever you have a differential equation where it's dy dx equals a constant times y, so it has to be the dependent variable here, okay? At the end of the day, you know that the solution is going to be y equals c e to the negative 5x. And again, here the x variable is t, here it's x. My point is, this is a really nice shortcut. If you ever have a differential equation equals a constant times the dependent variable, swing, you can just go right down here. The solution is going to be y equals c e to the negative 5x. And I said to someone, for an exponential growth function, when you sub in x equals 0, what does y equal? And everyone thought, oh, well, when x equals 0, I get y equals c. So I'm going to call this here, since population growth is often used, is often modeled exponentially, whatever this constant is, you can think of it as like your starting population, okay? So I called this shortcut the take it or leave it, but generous if you take it, because certainly you can always go ahead and solve the diffie-q. But what you're doing is, from here, you're spending about 2 to 3 minutes as opposed to just going, oh, I know, this will be boom. It'll always give me this. Okay? So now, let's use this for a second. I did a little bit of pre-cal. I said, okay, bacteria in a certain culture increase at a rate proportional to the number present. If the number of bacteria doubles every 4 hours, in how many hours will the number of bacteria triple? And what you're given here is, this is the model of bacteria growth. So y is the amount of bacteria, t is in time, okay? Y naught, this is the amount of bacteria when t equals 0. And we don't know what k is. So the first thing is, I'd like to be able to find what k is. I know that this constant here, it's some unknown, but it's y naught, it's the beginning population of bacteria. So the first thing I did here was, okay, the number of bacteria doubles every 4 hours. That means when t equals 4, the amount of bacteria will be double the starting amount. So I just subbed in 4, 2 y naught. And what this allows us to do, if you follow my pen here, is it allows us to then solve for k. K is ln 2 over 4. And now what's nice is that now I have my function. I have my actual function modeling bacteria growth. Y equals y naught e to the kt. And I found k, okay? And then you can ignore this purple, but we got a little bit of a tangent here, so just ignore all this. Someone asked a question about properties of logs, and I went on that tangent, but it's not going to be helpful to you. But now we can say, okay, in how many hours now will the number of bacteria triple? Well, okay, now I have my general equation, my general relationship. What is the value of t? What will t be when the amount of bacteria triples, okay? And now we're here, and now you can solve for t. I trust you know how to solve for t at that point. Okay? So the first part of this lesson was just revisiting exponential growth and decay and offering a shortcut, okay? Now, this second shortcut is with logistic models, and this is a shortcut that if you don't take it, you'll be in a world of pain. So I want you to follow my pen. So the first thing I want you to look at is when you have a differential equation that looks like this, okay? And just make sure you recognize, I should have written it here, that K and A are unknown constants. They are constants, okay? And if I look at this differential equation, now I rewrote it in terms of y and x because some people just like to see it in terms of y and x the first time through. But really, if you look at this differential equation, the differential equation is entirely in terms of y, right? Again, a and k would be just constants here. And I'm going to ask you, if I were to solve this differential equation, how would I solve this? I think hopefully you'd all say, well, separation of variables for sure. I'd have separation of variables, and then I'm just going to write this down. We're not going to pursue this, and I'll tell you why in a second. I would have ky times 1 minus y over a dy equals dx. Okay, and then if I were to continue solving, everybody, this side, when I anti-differentiate, super easy. Left-hand side, when I anti-differentiate, it's going to require what method, everybody? Partial fractions. And all I'm going to say to you right now is, this is a completely solvable differential equation by separation of variables, but the amount of algebra that presents itself is what is, I would call, a torrential nightmare. It is not doable. It is totally doable, but it is just so long. So what I want to offer you is a shortcut, okay? When you have a logistic growth differential equation, because that is what this is. This is a differential equation for logistic growth. Just like this here is a differential equation for exponential growth or decay, okay? This will always be a differential equation for a logistic growth function. Let me show you what a logistic growth function looks like. Walk over here to the axes, okay? Label your follow my pen, everybody. This is the x-axis, this is the y-axis. Look at dy dx. For what values of y will dy dx equal 0? Hopefully you'll say y equals 0 and also y equals a. Okay, what are those? Y equals 0 and y equals a will always be the two horizontal asymptotes, okay? A logistic growth function will always have this shape. Some people like to call it like a tangent function on its side. I get that, but it's not, okay? And you'll notice that a logistic growth function will always have a point of inflection. And this point of inflection will always occur at the y value that is 1/2 the upper asymptote. Again, I want to make very clear something. I never will tell you something in math like, this is true and just believe me, okay? Never ever. We derive everything. And I'm saying to you that this is completely derivable, but if we were to go all the way through and do partial fractions, believe it or not, we get partial fractions, we get disgusting parts along the way, then we have a disgusting u sub. It just takes too long. So this is what this differential equation will always yield, okay? This is the solution graph to this differential equation. And then, of course, we could ask some questions. Okay, what is the limit as x approaches positive infinity of y? Because I did use x and y here, okay? And you'll see here that the function here approaches a y value of a, right? But what is the limit as x approaches positive infinity of dy dx? What will the slope of the line tangent approach? That is 0, okay? So that's what we're talking. So that is a logistic growth. Now, this is a shortcut you must take, because if you don't take it, you will never have enough time to answer a question. So then I asked students, okay, kids, we'll go to the words in a second. The first thing I said was, please sketch this graph. Sketch the p as a function of t graph. Please go ahead and sketch it. And whenever you have a logistic growth function, you'll always be told that you're given a logistic differential equation. So that's nice, right? Okay. So go ahead and sketch this. And what most people saw was they saw, oh, the asymptotes are p equals 0 and p equals 240. Okay. P equals 120 needs to be P equals 1, I'll talk about the 2 in a second. P equals 120 is where the inflection point occurs. And then P of 0 equals 150. That just means like this y-intercept. So the first thing I did was look at the red. The first thing I did was I just threw the red thing down. I was like, okay, well, this is 150 here. This is 150 here. And then the inflection point has to occur at P equals 120. And very quickly someone said, wait, how can 120 and 150, like the y value is all messed up? And I was like, oh, right, we noticed that. So really what this is doing is it's a blue function. So 120 is still where the inflection point happens, but the y-int is at this point, 150. That was kind of a good observation. Okay? And for what value of P is the population growing the fastest? Well, it's at P equals 120. Okay? Here's another one. Here's number 2. Now, number 2, it's this differential equation is not in the form that you're used to, but you're told it's logistic Diffie-Q. So the first thing I challenged the students was I said, okay, well, here's what I want you to do. Make this logistic differential equation, since you're told it, make it look like the form, a form that you're used to. So I get a 1 here. And very quickly they said, oh, I'm just going to factor a 3p out. And they got this, okay, which then allows you to graph asymptote at P equals 5,000, P equals 0. The point of inflection here is at 2,500. And I guess we can say here P of 0 is 1,000. That means this value is 1,000 if I wanted to put more information. Okay, and here's what is the limit as T approaches positive infinity of population? Well, the population is approaching 5,000. Okay? So that was logistic Diffie-Q. That is the lesson that you missed. We did some of this as well. There is a typo here, so you can make this should be P of 0 is 10, not 100. So make that change. All right. You can go ahead and do this page, and then that was it, kids. All right. Goodbye.